First speaker of the afternoon, it's a pleasure to introduce Taras Panov, who will talk about polyhedral products, graph products, and P-central series.
Thank you very much. So I'll talk about some relationship between polyhedral product of topological spaces and graph products of different algebraic objects, and most prominently groups. And basically, there were two series of results, parallel, one about some graph products, in particular right-angle groups, right-angle Artin and Coxeter groups, and then another one about coming from homotopy theory of polyhedral products, which basically describes loop homology of certain polyhedral products. And there seems to be some very nice relationship between those two series of results. And we would like to develop some kind of translator, some technique which allows one to convert results of graph products of right-angle groups into some homotopy theoretical results about loop homology and vice versa. And it turns out that one of the possible techniques is this P-central series and the Lie algebras, P-restricted algebras associated with this central series. So this is a joint work. This last bit related to P-central series is a joint work with Timurbek Rahmatullayev. So I'll briefly remind what the polyhedral product is. In the standard setting, you start with a collection of topological spaces, M pairs of topological spaces, and a simplicial complex on M vertices. And then you form this product of smaller spaces and bigger spaces for every particular set of indices. So it's a product of y1 through ym, where yi is the bigger space if I is in your set, and it's a smaller space when I is not in your set. And then you take the union of all those things over the simplices in your simplicial complex. That's what's called polyhedral product over simplicial complex. And that works with topological spaces. So just to fix the notation, we use this polyhedral power notation. So x to the power k will denote just x comma point to the power k. So you may have a sequence of spaces here or a single space. So we use this abbreviated notation for this polyhedral power as opposed to the general polyhedral product. So then, well, you can, there is a categorical setup for this construction. It's really light, so it's not really hard category theory. So you just start with a small category of faces of your simplicial complex. It's a poset category. It has at most one morphism between two objects. So there is a morphism when there is an inclusion of faces or simplices in your simplicial complexes. And then you look at the big category of topological spaces, and you could look at a functor or diagram from poset category to topological spaces, which assigns to your simplex this product of x and i's, x and a's. And it maps morphism, the inclusion, into the inclusion. So then you take colimit. So that union of products inside the product of all x's is actually the colimit of topological spaces, a nested union. So you're taking, what you are doing is actually taking colimit of this functor, of this diagram. And well, then once you wrote this, you can instantly observe that you can do the same sort of construction in arbitrary model category. In arbitrary, you don't need model, just symmetric monoidal category with finite colimits. So you just, in that construction, you just need, if you go back to this one, so you see here, you need products and you need colimits. That's all you need from your category to form this analog of this polyhedral product. So you can do it in any symmetric monoidal category with colimits. So it's well, it's just a repetition. So you start with a simplex, a sequence of, yeah, you can do pairs as well if you wish, but let's stick to just one sequence. And so you have a sequence of objects, you form product with respect to your monoidal structure, and then you look at the similar diagram, which maps the inclusion to the canonical morphism. So here you need a monoidal unit in this to define, so that the analog of point, of the base point of topological spaces to define this morphism. And then you can take this polyhedral product in your C, in your category C, as a colimit of this diagram. Yeah, so that's very straightforward analogy with the original construction of spaces. And actually, what you can observe is that there is, well, I mean, in group theory, this leads to what's called the graph product. And in topological spaces, that's called the polyhedral product. And you can observe the following difference between this topological and algebraic setup, that if you consider the one particular simplicial complex, the boundary of a simplex, or in combinatorial terms, all proper subset in a set of M indices. Geometrically, this is a boundary of a simplex. Then, if you do a polyhedral product of spaces, then what you get is what's called in homotopy theory the fat wedge. And of course, if M is just 2, then the polyhedral product of topological spaces is an ordinary wedge. But that's fat wedge, which is important here. Now, and you say that a symmetric monoidal category with finite colimits is fat if the fat wedge is a product, right? So when this canonical inclusion of this polyhedral product from the boundary of simplex to the simplex, so this polyhedral product is just the product of all x's, and you want that to be an isomorphic, then you say that your category is fat. For M greater or equal to 3. So you want to have ordinary coproduct, of course, but when you start taking analogs of fat wedge, then there is nothing interesting happens, basically, right? So that's what a fat category.
When does that ever happen?
Yeah, I'll show you in a second. Yeah. That's happened too much often, much more often than you expect. So that's here as example of fat categories. So basically, if you just do algebraic category without resorting to any model structure, without resorting to without adding some differentials or so on. So you do groups or topological monoids, topological groups, associative algebra or Lie algebras. These are all symmetric monoidal categories. And in all of them, what you observe in each of those categories, if you have a set of pairwise commuting elements, then they generate a commutative subgroup. So all those categories are fat, if you think of that. But on the other hand, the category of topological spaces is clearly not fat. There are fat wedges of topological spaces, but there are no fat wedges of groups or associative algebras. Right. So, and that has some consequence. So if you think if you try to build up a polyhedral product of groups over the boundary of a triangle without the interior, then you get the same thing as if the interior was there. Because if those elements in the group commute pairwise, then they commute totally, right? So and then, well, you can kind of elaborate on that and say that in a fat category, the morphism, so you can form this polyhedral product, and if your category is fat, then it depends only on the one skeleton of your simplicial complex. So this K1 denotes the one skeleton. So whenever you have this morphism is an isomorphism for any simplicial complex and any sequence of objects in a fat category. So that leads to the following terminology. So if you have a simple graph without loops or double edges, then you can form a simplicial complex out of your graph. It's called the click complex or the flag complex of your graph, whose simplices are complete subgraphs, cliques. Then, of course, that's the click complex is not the same as a graph, but there is a one-to-one correspondence between them. So every graph gives you a click complex, which is a flag complex, and every flag complex is a click complex of its one skeleton. And so you can define the graph product for a sequence of objects in your category. If you think in terms of polyhedral product, that what you are doing actually is to define this x to the power gamma, it's a graph product, you take the polyhedral product of the click complex. And if your category is fat, like in all those algebraic cases, then this graph product is canonically isomorphic to the polyhedral product for any simplicial complex whose one skeleton is your graph. So this, but that you can define in any category. This graph product, it's just the polyhedral product of the click complex. But your category is fat, it becomes somehow much simpler. And of course, yeah, the standard, the most well-known example is a graph product of groups. And so you start with a sequence of groups, not necessarily discrete. You can do topological groups as well if you want. And that will be important. And so since the category of group is fat, you have this identification. So this polyhedral product is the same for K1, or this is a graph product. So it's a colimit of product of your groups over the simplices in your simplicial complex, or over cliques in your graph. And well, that's a categorical definition, but you can write it explicitly as a quotient of the free product of group by commuting relations. And so you need to actually, you can write down this quotient. You take the free product of all your groups and you impose this commutativity relation. So the elements in different groups commute whenever there is an edge in your simplicial complex. And then you can check that this gadget actually has a universal property of the colimit. So it is a graph product. And also you have this canonical injective homomorphisms from the products of your groups over any subset to your graph product. So that graph product somehow if your simplicial complex is a discrete set of points, then you get a free product. And if it contains a complete graph, then you get the Cartesian product. Then you have something between them. Like the polyhedral product of topological spaces sits between the wedge, m-fold wedge, and m-fold product. This sits between m-fold free product and m-fold Cartesian product. Right. So, well, then you can ask. You can have you have different functors between those categories, or between one category may be fat and another not. And you can ask when some functor preserves these graph products. And this is certainly the case when your functor preserves finite products and colimits, right? Because that graph product is a combination of finite products and colimits. But there are other nice examples. Basically, there are classifying space functor and the loop homology. So we'll go through this next. So you have this classifying space for G and the universal G bundle, EG to BG. So here G is maybe discrete group, maybe topological group, doesn't matter. So you have this, then you can form the topological polyhedral product out of the classifying space for your groups. So this one, so you take, so obviously, yeah, I mean, the classifying space functor preserves products, so you can write the classifying space as a product group is a product of classifying spaces, and then you can form this polyhedral product corresponding to this sequence of pairs of topological spaces. And similarly, you can do another pair, EG, G, where each group is now viewed as a topological space. So if it is a discrete group, that's just a discrete set of points. And it's included in this universal space as a fiber of this bundle over the base point. And then you have this fibration of polyhedral products. So this is just the inclusion of the polyhedral product into the product of the product of all BGs, and that fiber of that is this polyhedral product. Right, so and well, of course, the classifying space functor from topological groups to topological spaces, well, you need to do well-behaved topological groups, like well-pointed. You need to be careful a bit, slightly careful about this, but still, there is a model structure on the category of topological groups, and well, so you can observe, you can pick up your favorite example where this classifying space functor doesn't preserve colimit. And well, that's one of the, if you think about this one, that you'll see, that's the first source of examples. And but it does preserve homotopy colimits under appropriate model structures of topological groups. So we had that theorem with Rainer Vogt in the beginning of 2000. So you can do homotopy colimit of topological groups, and then you can classify that, and it turns out that there is a canonical map from homotopy colimit of spaces to homotopy colimit of topological groups, and it's a homotopy equivalence. And obviously, there is another map from homotopy colimit of topological spaces to this polyhedral product, which is a colimit of topological spaces. And that construction of the topological polyhedral product, you can do it either with colimit or with homotopy colimit. That diagram that I showed you at the beginning over the cut K in topological space, that's kind of ready cofibrant. So that for that, you can do either colimit or homotopy colimit. They're all the same. So that's a property of the polyhedral product of spaces. But this is not the case for groups. For groups, for topological groups, the colimit is this graph product, and the homotopy colimit is something different, generally. So those two arrows are always homotopy equivalences, but those two are not. And in fact, they are if and only if K is a flag complex. If and only if your polyhedral product is a graph product. So this last bit can be restated by saying that, so if you look at this lower arrow, then it's actually a map from BG to the power K from the polyhedral product of spaces to the classifying space of the graph product of groups. And as a corollary of this, you get that this is a homotopy equivalence for a flag complex, and therefore you can say that the classifying space functor preserves graph products up to homotopy. Yeah.
Where is flag used?
The flag is used when you show up this homotopy equivalence. Well, that's not a. So I mean, if K is not flag, then you can easily see that this lower arrow is not a homotopy equivalence, because like this, spaces have much more structure because of the presence of those fat wedges. I mean, once you have an empty triangle, then you had to get a fat wedge which retracts of this one, but here you just have a product of groups. So that cannot be homotopy equivalence once you have at least one empty simplex of dimension larger than 2. But yeah, that this one is a homotopy equivalent. That's something to prove here, and it subsumes all some in the discrete. G can be a discrete group case, and that somehow subsumes several known examples of when the graph product is in a spherical space for a Flagg complex. Yeah, so that's included that, and it works for topological groups as well. So in particular, that means if you started with a set of discrete groups, then that in particular means that this polyhedral product is in a spherical space, because the graph product of discrete groups is a discrete group, and therefore its classifying space is a k-pi1 space. So that also implies that this polyhedral product is a k-pi1 space. So, right, so let's do some examples. Two prominent examples of graph products are right-angled groups. The right-angle arcing group corresponds to the case when all your groups in your sequence are integers, a group of integers, so infinite cyclic group. Then this graph product is a quotient of the free product of m copies of Z. That's a free group on m elements modulo these commutativity relations. It's known as a right-angle arcing groups in geometric group theory, or just in combinatorial group theory. It's sometimes called partially commutative group. So it's partially commutative. Some of the generators commute, some do not. And well, from that analysis that I showed in a previous slide, you know how to write down that, since you've written a group as a polyhedral product, as a graph product, you know how to write down its classifying space, its k-pi1 space. So you just take the classifying space of each group and take the polyhedral product. So that's a polyhedral product of circles. It's a sub-complex of an M torus, and it was known for quite a while, since the beginning of '80s, that this sub-complex, originally it was done in the work of Kim and Drush, that's the classifying space for the k-pi1 space for the right-angle arcing group. And if you look at that homotopy fibration that we had, this one. So all those examples I'll also write down this homotopy fibration for all those things. So that one would be like this. So this is a polyhedral product, which is a kernel of this inclusion map. And all these spaces are spherical, because you start with a discrete group. So here K is Flagg right from the beginning. So now once you pass to the fundamental groups, you get this exact sequence, short exact sequence, where this is a commutator subgroup. So you also know that this space is a k-pi1 space for the commutator subgroup in a right-angle arcing group. Okay, now you can do the same thing with the right-angle Coxeter group, which is a graph product of cyclic groups of order 2. So now you have, this is a graph product, and this is a presentation, explicit presentation, the quotient of a free group by these relations. So now you have partial commutativity relation, and also the square of each element is 1. And then the classifying space for this one, or the k-pi1 space, you just need to classify each group. So that gives you RP infinity, and then takes the graph product. And similarly, if you do E Z mod 2, Z mod 2, then that E Z mod 2 is just a point, and Z mod 2 is just 2 points. So basically, you can turn this map into a you can replace this E Z mod 2 with something homotopy equivalent to it. You can take the simplest case as just one disk, and so you see that this polyhedral product is actually homotopy equivalent to the polyhedral product of a disk and circle, of a segment and 2 points, which is sometimes called the real moment angle complex. It's just a cubical complex, a subset in the M cube. And so you have this homotopy fibration, again, in which all those spaces are spherical. And this is now, unlike the case with arcing group, this is a finite CW complex. So it's a subcomplex in a cube. And again, passing to the fundamental groups, you get this exact sequence where this one is a commutator subgroup of a right-angle Coxeter group. So these are the two most well-known graph products, but you can also do topological groups, as I said. So you can take, instead of 2 points, which sometimes it's called like a real torus. You can take a complex torus, well, in a sense, a circle. And then you can also form this graph product, and now it's some huge non-commutative topological group, colimit of tori, colimit in the category of non-commutative topological groups, obviously. So it's called circulation group. And its classifying space is a Davis-Januszkiewicz space, the polyhedral product of CP infinities. And you have this homotopy fibration. So that polyhedral product is homotopy equivalent to the moment angle complex. And then you have this homotopy fibration. And if you loop it, then you get exact sequence of topological monoids. If you do Moore loop space, then you get a topological monoid, and you have this sequence, and you can think of that loops on the moment angle complex as a commutator subgroup in your circulation group. Okay, so, and well, once you've understood this example, you can generalize that to just arbitrary polyhedral product of the form x comma point. So if you take as GI the Moore loop monoid of a simply connected space, then you have, by classifying that homotopy equivalence from bg to the power k to b of g to the power k, you can classify this homotopy equivalence and you get an equivalence in the homotopy category of topological monoid. So the loops on this polyhedral product is the same as a graph product of this particular monoids. So again, you can say that the Moore loop functor preserves graph product up to homotopy. All right, so that was about groups and monoids. Now you can do algebras as well. So associative algebras first. So if you start with if you look at the homology of the loop space with coefficient in some commutative ring with unit, then it is an associative non-commutative algebra with respect to Pontryagin product. You get a functor from topological spaces to associative algebras. And in fact, this is not just an associative algebra if you walk over a field or when your loop homology is free over R, it's actually a Hopf algebra because you have this diagonal map which makes it into a co-commutative Hopf algebra. So, right, so now you can do the same business with associative algebras. You can form a graph product using the monoidal structure on associative algebra, where the product is a tensor product. So in groups, the product was a Cartesian product. Here, the product is, you look at the monoidal structure with respect to the tensor product. So now you can take this colimit of associative algebras, and well, you can also observe that the category of associative algebra is fat, and then you have that generalization of all those examples, which was that was originally stated in a preprint by Natalia Dobrinskaya, but with a hint of proof, I would say. And now recently there was a paper of Litzai where that was proved in a thorough way. So if you start with a Flach complex and a sequence of simply connected spaces over a field, and you walk over a field, then the loop homology of polyhedral product is a polyhedral or graph product of loop homologies. You can write it explicitly like this: take the free product of those non-commutative associative algebras and mod out these convertibility relations. So again, this can be restated by saying that the loop homology functor preserves graph products. So now you have enough sort of functors that map between different gadgets, different polyhedral products or different graph products. And you can actually prove something out of this, just out of the merely functorial properties of these functors, of these constructions. So, well, the particularly important cases are odd-dimensional spheres and infinite dimensional projective spaces. So, because like the loop homology of an odd-dimensional sphere is a polynomial algebra in one generator of even degree, and so if you do the appropriate graph product algebra, you can think of it as an algebraic counterpart of the right-angled arcing group. And so there is a theorem which is just a manifestation of this previous more general result, but it's in this particular case, it can be stated in a much nicer way. It's due to Peter Bubenik and Lea Gold. So for any flag complex, the loop homology algebra of this polyhedral product of m-dimensional spheres, it doesn't matter where you put parentheses here, right? Because everything is preserved, that this polyhedral product are preserved. So that's the graph product of polynomial algebras. And explicitly, this is this, as I said, this is like algebraic analog of a right-angle arcing group. So now instead of group generators, you have associative algebra generators, you have a free tensor algebra, and you mod out by commutativity relations. So the two generators commute whenever there is an H. Right, so that's a perfect analogy between the right-angle arcing groups and these partially commutative associative algebras. And in this particular case, it's worked perfectly. And you can try to model that analogy in the case of right-angle arcing group, or in the case of, sorry, right-angle Coxeter groups. And it also worked up to some extent, but not quite. So now if you replace this odd-dimensional sphere with an infinite-dimensional projective space, then you have this loop homology of the Davis-Januszkiewicz space. And you can think of it that it's similarly related to right-angle Coxeter groups. So, yeah, so you just first look at the loop homology of the BTM, the classifying space for the M torus, or the product of M infinite dimensional projective spaces. And this is just the homology of the torus, M torus. So this is an exterior algebra on M generators of degree 1. And then when we looked at this homotopy fibration, and first we just looped that, and we got an exact sequence of topological monoids, of Moore loop monoids. Now you apply loop homology, so you get an exact sequence of associative algebras. Well, you need to make clear what do you mean by an exact sequence of associative algebra. So you can do either Hopf algebras if you are over a field, or you can do what's called the normal subalgebra. That means that this is a normal subalgebra here, and the quotient is this one. So in other words, you can say that this loop homology of the moment angle complex is a commutator subalgebra of this loop homology of the Davis-Januszkiewicz space. In a way similar to that, the loop homology of the real moment angle complex is just a commutator subgroup, right angle Coxeter group. And we have a similar theorem about this loop homology, that it tells you that the loop homology of the Davis-Januszkiewicz space is also like a partially commutative algebra, but this times you have like partially commutative exterior generators. You have an extra relation where ui square is 0. So all squares are 0, and some of them anti-commute. And all of them are of degree 1. That's for flag complexes. If K is not flagged, then this loop homology is much larger. It contains all those kind of higher commutator products, Gurevich images of high Whitehead product, but it still contains this partially commutative subalgebra. And well, that looks like a right-angle Coxeter group. It's an algebraic counterpart of the right-angle Coxeter group. And well, there is a further manifestation of this analogy, right? So that's kind of a translates to saying that that thing is an algebraic analog of right-angle Coxeter groups. And if you look at the commutator subalgebra, so this is a commutator subalgebra, and you can look at the commutator subgroup in the right-angle Artin group, in the right-angle Coxeter group, and they also behave in a similar way. So there is a pair of theorems, for instance, describing the commutator subalgebra in this loop homology algebra and the commutator subgroup in the right-angle Coxeter groups. They are similar descriptions of a basis. And also there is the same criterion when this commutator subgroup is free, for instance. And so looking at those two things, you would like to produce some kind of way to translate, say, group theoretical result into homotopy theoretical results about this loop homology. So you want, so things, this somehow related to some functor preserving loop homology. You want to find out some better functor which maps one thing into another. And so you can, once you get something about, you know something about the group structure, you can say instantly something about the loop homology and vice versa. Well, that's in general, that looks like too complicated for a program, but there is some particular examples where it works well. And it's related to the third part of my talk in my title, this central series. So one of the tool is a central series of a group and also the associated Lie algebra of those central series. And so I just go briefly through that. That's the standard. So you have, if you have two subgroups in a group G, then you have this commutator subgroup generated by all group commutators. I denote the group commutators in this parenthesis, and there'll be Lie commutators which will be square brackets. So, and you have the notion of a central series or central filtration on a group is just a series of subgroups, descending series of subgroups, such that this commutator subgroups of K's group in your sequence and the L sits inside of K plus L group. And out of those central filtrations, so central means that the consecutive quotients of this filtration are abelian groups. And you can look at the fastest descending central series. It's known as a lower central series. So that's defined like this. And the important thing about that is that first, of course, you can, if you take the associated graded object of this filtration, then it's an abelian group. But more than that, it's not just an abelian group, it's a Lie algebra. So that is on this associated graded object, so if you take the sum of all those subsequent quotients, these are all abelian groups, you can put a Lie bracket onto that. So the Lie bracket is defined in a very naive way, but of course you need to check that this is a Lie bracket, and that's what's called the commutator calculus. So you just say that you take two elements in G in this quotient group, you take representatives in the appropriate subgroups, and you commute them. You take the group commutator, and then you take it turns out that this group commutator goes down to the filtration, so it sits actually in the K plus L term, and then so you can take its representative, and that satisfies the Lie relations, the Jacobian identity, and so on. That's a Lie algebra. Lie algebra over Z, so it's a Lie ring sometimes it's called. And by the classical result of Magnus, if you apply this construction to the free group, then you get free Lie algebra. That's one of the basic of the combinatorial group theory. And this can be generalized to right-angle Artin groups. So the theorem, which originally is due to Duchamp and Krob, but there are several other proofs, one in particular in the work of Papadima and Suciu, so that if you look at the Lie algebra associated with a lower central series of a right-angle Artin group, then you get precisely this partially commutative Lie algebra. So this means a graded Lie algebra associated with a lower central series of a right-angle Artin group. And it has precisely the same relation. So you just convert the commutator relations into the Lie relations. That's how you write down the free Lie algebra. And furthermore, each graded component is a free abelian group. So this is what's called graph Lie algebra or partially commutative Lie algebra. And once you work with graph products, then you realize instantly that it is also a graph product. It's a graph product of trivial Lie algebras on one generator. So you take trivial Lie algebra, but then you take colimit, so it's no longer trivial. So it only has some partial commutativity. All right. So now, how you can interpret that result in terms of the graph products? So, well, you can look at the universal enveloping functor from Lie algebras to associative algebras. And that universal enveloping functor, it preserves graph products for obvious reasons, because it's left adjoint to the forgetful from associative algebras to Lie algebras, and it also preserves product, so it preserves graph product. So you can write it, you can apply it to this Lie algebra, and you write the tensor algebra module of the same commutativity relations. That's what it tells you. So now, this is just a reformulation of that two results of Dusham and Kromp and of Bubenik and Gold, that if you start with a right-angle Artin group and apply a series of functors, each preserving the graph product. So first you take this lower central series, and then you take its universal enveloping algebra. So you get a loop algebra of odd-dimensional spheres. So that somehow translates algebra into homotopy theory, so via this applying this lower central series. Right, so that's fairly straightforward, and then you're okay. You try to apply it to right-angle Coxeter groups, and then you fail for some interesting reasons. So, okay, then try to do this for right-angle Coxeter group, and at the first planes you are very enthusiastic, because you find instantly that if you do the lower series for right-angle Coxeter groups, if you think a little bit, then you observe the following interesting property, that the square of an element in the case component of a lower central series sits in the k plus 1's component. Right? So this is basically like a nested commutator of length k, and if you square that in your group, then you can rewrite it as an iterated commutator of length k plus 1. As a product of iterated commutator of length k plus 1. So what does it tell you on the language of associated graded object? That basically the quotient, in the quotient of gamma k modulo gamma k plus 1, every element is of order 2. Because like this passing to this associated graded object, it converts, that's kind of the fundamental ideology of Magnus, it converts products into, group product into the sum operation in the Lie algebra, and it converts group commutator into the algebra commutator. So this is a group product, the square becomes just the sum, and so every element has order 2. So this one is a Lie algebra over Z mod 2, and then you say, okay, well then that should be like the free Lie algebra over the mod 2 modulo the same commutativity relation. But this is not true, right? Group theorists would say that that cannot be true, of course. So you have just a surjective map from this quotient now over Z mod 2 to this associated graded object of the right-angle Coxeter group, but it's not an isomorphism. Already when you have two disjoint points, then it turns out that this is a finitely presented Lie algebra, but this one is not. It has infinitely many relations. It's in a sense smaller. So it has kernel, that map. So there can be no analogy with this isomorphism when you work with ordinary central series. And the idea, well, okay, then there is some, but once you have groups in which elements have prime order, then you should look at some other central series. They're called p-central series. And there is a related notion of restricted Lie algebras. So that's still an interesting problem. I mean, it's so how to write down this associated Lie algebra associated with a lower central series of a right-angle Coxeter group. Yeah, and very interesting problem, but it looks very hard. So if you want to relate that to this loop homology, then you proceed in a different way. You look at what's called restricted Lie algebras, and I'll just go briefly through that. So it's like an Lie algebra together with a p power operation. So you work now over a field of characteristic p, and in the associative algebra over field of characteristic p has this p power operation, which is nice, and it has some nice property, and then you model those nice property in a Lie algebra. So that's kind of those properties which are satisfied by the p power operation in an associative algebra over a field of characteristic p. So that's called restricted Lie algebra. It's a Lie algebra together with a p power operation. So yeah, that's. Sorry. And then you can have a special central series which fits well with this p power operation. It's a central series, so with additional properties that the p's power of an element in the case graded component, in the case component in the case filtration belongs to p times k filtration. And so once you have this, then the consecutive quotients are not just abelian group, but the Z-mod p modules, and you can write down the associated graded objects, and you have this analog of the fastest descending series, which you can write down explicitly. And once you start with a group and look at its associated graded object associated with a p central filtration, then you get a restricted Lie algebra together with a power operation. Right, so now you can apply that to the right angle Coxeter groups, or even more generally to the polyhedral products of, yeah, I need to finish just briefly. So you start with this, you define this polyhedral product of elementary abelian p groups, or just Z-mod p in a similar way. And then that theorem is that actually, if you apply to that the p central, lower p central filtration instead of just central filtration, then you get what you expect. You can write down this associated graded algebra as a graph product. So that uses some equivalence techniques of comparing the two filtrations. The one is the one defining this lower p central series, and another one is a filtration in the group algebra by the power of the augmentation ATO. And the corollary of this is that first, that this graded Lie algebra associated to the lower p central filtration preserves graph product of elementary abelian p groups. And if you apply it to the right angle Coxeter groups, you get this explicit presentation for the associated 2 Lie algebra. And you can restate that topologically by saying that the universal enveloping algebra of this 2 Lie algebra is the loop homology of the Davis-Janusz-Cage space. Yeah, so that somehow allows you to some extent to convert group theory into homotopy theory of loop homology. Yeah. Okay, so I'll stop here. Thank you.